Okay, let's jump right in. Today we're looking at a really interesting paper, Scaling Agent Learning via Experience Synthesis. This one's by Chen and colleagues from Meta, UChicago, and UC Berkeley. For anyone needing the quick version, here's the core idea in about a minute. Training LM agents with traditional reinforcement learning, especially in complex places like WebArena. It's often a non-starter. Why? Well, you've got super high costs for running interactions, rewards that are few and far between, and it's just hard to find, diverse and scalable environments. So the solution proposed here is called DreamGym. Think of it as a unified system that cooks up agent experiences synthetically, purely online. It uses this clever reasoning-based model, they call it MenXBay, that works in an abstract text space. And it uses chain of thought reasoning to make sure the state transitions and the feedback it generates are actually consistent. The results, pretty staggering. DreamGym makes RL work where it really didn't before, like WebArena getting like over 30% better performance than the old methods, and maybe even cooler, their sim-to-real technique, DreamGym S2R, gives a massive head start. We're talking over 40% performance boost while needing less than a tenth of the real-world data. Pretty wild. All right, let's dig into this properly. The paper kicks off by really laying out why standard RL just hits a wall with these modern LLM agents. What are those big blockers?
Yeah, they outlined four main practical hurdles that DreamGym is basically built to overcome. First, and maybe the biggest one, is just the sheer cost and sample inefficiency of real-world rollouts. Think about it. If you have an agent trying to, say, book a flight on a real website, each attempt involves a long sequence of actions. That's computationally heavy. And often you only find out if you succeeded or failed right at the very end. That's sparse reward feedback. Makes collecting enough data for modern RL algorithms just incredibly expensive.
Right. And when you say expensive, like, how much data did the baseline methods they compare against actually need?
Well, in Table 1, they mentioned baselines needing up to 80,000, that's 80,000, real interaction steps just to get algorithms like PPO or GRPO to show even, some learning.
Wow, 80K steps. And that's probably for relatively constrained tasks, right? Scaling that, forget it.
Exactly. Which leads straight into the second problem, limited task diversity. Most existing testing environments have static tasks. If you want your agent to handle new goals, you often need a human to check if the goal is even possible in that environment. Trying to scale that up, maybe for goal-conditioned RL, it becomes a massive human bottleneck.
Okay, so collecting data is slow, creating good tasks is slow, and then there's the whole reliability issue, which I think really spooks people about using dynamic environments.
That's the third one, unreliable reward signals. Real-world systems like web pages or GUIs, they change. They aren't perfectly predictable like, say, a game physics engine, so the feedback the agent gets can be noisy or way too sparse, or sometimes just plain wrong, false feedback. That can completely derail learning.
And safety, too, right? Like clicking the wrong button could have real consequences, or you can't even reliably reset the environment state sometimes.
Precisely. Irreversible actions, no guaranteed reset function. It just adds layers of complexity and risk. And the final point is more on the engineering side. Infrastructure complexity. Running these interactions, especially in parallel for large batches, you often need complex setups, maybe involving Docker containers or VMs for each instance. Managing all that diverse infrastructure for large-scale rollouts is a huge engineering lift, and it costs a lot. DreamGym is essentially trying to bypass all of that.
Okay, so this is where DreamGym comes in, and it's a really clever shift in thinking. Instead of trying to perfectly simulate the physical world, it focuses on generating the experience the agent needs. The key insight seems to be that the agent doesn't need raw pixels or HTML. It needs data that's informative and, crucially, causally sound. Is that right?
That's exactly it. The core is this reasoning experience model, the MXPure. It doesn't simulate the messy reality directly. Instead, it abstracts the environment's dynamics into a much cleaner, discrete, textual meta-representation.
Let's pause there because that abstract space feels like the secret sauce. What does that actually mean in practice? How is it better than just using the raw web page data, for instance?
Okay, so imagine a web page. Instead of the model seeing like the entire HTML structure or a screenshot, MyXpand generates a simplified list of the important elements. Maybe the buttons, input fields, key text snippets. It strips away all the unnecessary layout stuff, the noise. It's like getting the instruction manual instead of the full messy machine.
Ah, I see. So it's a filtered, much more focused view.
Exactly. And that's why it's so sample efficient. Figure 5 in the paper shows it gets really competitive performance using only maybe 2,000 to 10,000 offline samples for training more month. Compare that to the 80,000 real steps needed for the baselines.
That's a huge difference. Okay, but if MAMXB is just making up the next state, how do you stop it from, well, hallucinating? How do you ensure the synthetic steps actually reflect some kind of consistent reality the agent can learn from?
Right, that's where the chain of thought reasoning comes in. It's absolutely critical. When Members predicts the next state, MICTI plus Lebon, and the reward, Members C plus Onegger, it doesn't just output them. It also generates an explicit reasoning trace, like a step-by-step explanation for why that state transition and reward happened based on the action taken.
So it's forced to justify its predictions.
Yes. And to make those justifications good, the model looks at three things: the history of the interaction so far, the overall task construction, and this is important, similar past experiences it retrieves from a memory buffer.
Okay, so the model isn't just spitting out data, it's spitting out data with the reasoning attached, and that reasoning process itself helps keep the data grounded.
Precisely. The way they train ADAMs uses supervised fine-tuning, specifically with an objective they call lawless FT. This objective makes the model learn two things together. First, to generate good, faithful reasoning traces from their notation. Second, to use those reasoning traces to predict the next state accurately and consistently. That grounding in reasoning is what makes the synthetic data useful for training the agent.
And that retrieval part you mentioned, that ties into the memory and grounding component, the experience replay buffer.
Correct. That buffer is key for keeping the experience model factual, especially on knowledge-intensive tasks. It starts seeded with some offline data like human demonstrations from benchmarks, say the WebArena leaderboard data, but then it's constantly updated with new synthetic trajectories generated by memory itself. So the buffer kind of co-evolves with the agent. When MAM asks to predict a tricky state transition, it retrieves the top CAC most similar demonstrations from this buffer. Seeing how those real interactions played out helps it avoid making things up, reducing hallucinations.
Okay, makes sense. We have this efficient synthetic world model that uses reasoning and memory retrieval to generate consistent, grounded experiences. But agents learn best when challenged. How does DreamGym stop the agent from just mastering the easy stuff and getting stuck?
Good question. That's the third piece, curriculum-based task generation. The experience model, Mary SCAP, actually wears a second hat. It also acts as a task generator, and its job is to specifically generate tasks that are likely to be most valuable for the agent's current learning stage.
How does it know which tasks are valuable?
It uses a pretty neat heuristic based on group-based reward entropy, which they denote as VALIAT. Basically, it looks at the agent's recent performance on different types of tasks.
Entropy. So it's looking for tasks where the outcome is uncertain.
Exactly. Phi entropy means the agent is sometimes succeeding and sometimes failing on that type of task. There's variance in the outcomes. That's the sweet spot for learning the task is feasible but not solved. It provides the maximum information for the agent to figure out what works and what doesn't.
Right. If entropy is 0, the task is either too easy, always success, or too hard, always failure. So not much to learn there.
Precisely. Low entropy means boredom or impossibility. High entropy means maximum learning potential.
And did they show this curriculum part actually matters, like in the ablations?
Oh, absolutely. Table 2 shows a significant performance hit when they turned off the curriculum generator. Performance dropped by about 6.6% in WebShop and 6.0% in WebArena. Without that adaptive task generation, the replay buffer just fills up with the same old easy or impossible tasks. The agent stops exploring effectively and learning stalls.
Okay, so the architecture seems really well thought out. Synthetic generation, reasoning, memory, curriculum, it all fits together. So let's talk results. Did this complex setup actually pay off? What did they see on the benchmarks? They tested across a few models, right? Llama, Quinn.
Yeah, Llama 3.23b, Llama 3.18b, and Quinn 2.57b. And they tested on diverse environments. We can break down the results from Table 1 into maybe 3 key scenarios. First, environments that are basically not RL ready with traditional methods like WebArena. It's just too complex, too sparse. Here, DreamGym was essentially the only way they could effectively apply RL. And it didn't just work, it gave them over a 30% boost compared to all the non-RL baselines they tested, which struggle with exploration in that kind of environment.
Okay, so it unlocks RL for previously intractable domains. That's big. What about environments where RL is technically possible, like WebShop or ALF World?
Right, so the second scenario is looking at those RL-ready environments, but using DreamGym in a pure synthetic mode. This means zero interaction with the real environment during training, and this is maybe the most stunning result. DreamGym, trained only on its own synthesized data, achieved performance basically on par with standard RL algorithms like GRPO and PPO.
Which needed 80,000 real interactions.
Exactly. DreamGym matched them using zero real interactions. Just think about the implications for cost and speed of training.
Yeah, that's a game changer. Matching 80K real steps with zero. That completely reframes the economics of training these
It
agents.
really does. And the third scenario builds on this. Sim to real, which they call DreamGym S2R. Here, they first train the agent purely synthetically within DreamGym to get a good starting point. Then, they fine-tune it with just a tiny amount of real data, only 5,000 steps in their experiments.
Okay, a warm start strategy.
Right. And this hybrid approach consistently smashed the performance of training agents from scratch, using only real data. They reported over 40% improvement on some metrics compared to just training in the real environment from the beginning.
That's huge for practical deployment. It shows you can get most of the way there with cheap synthetic data, then just polish with a little bit of real-world experience. What about the overall efficiency gains, like total training time, compute?
Figure 3 addresses this. Because the synthetic rollouts in the abstract space are so much lighter and the feedback is denser, thanks to the curriculum, DreamGym cut down the total training effort that's rollout sampling plus GPU time to somewhere between 1/3 and 1/5 of what the real RL baselines needed. Massive savings.
And did the agents train synthetically generalized? Could they handle variations or transfer to related tasks?
Also shown in Figure 3, pretty strong generalization. For instance, an agent trained purely synthetically on web shop tasks could then be evaluated on WebArena, and it actually outperformed baseline models that were supervised, fine-tuned directly on WebArena data.
Interesting. So learning in that abstract space seems to teach more robust, transferable skills, at least within similar domains.
Yeah, it suggests it's learning some fundamental interaction principles, though they do acknowledge a limit transferring to a very different domain, like the embodied tasks in ALF world, was much less effective. The domain gap was likely too large there.
Okay, understandable. And stability. RL training curves can be notoriously jumpy. How did DreamGym look?
Much smoother. Figure 3 again. The DreamGym training curves show significantly less variance and more stable improvement compared to the traditional RL baselines. Those baselines often suffer from big oscillations, likely due to the noisy, sparse rewards from the real environments. Replacing that with DreamGym's consistent, reasoned synthetic feedback seems to stabilize the whole process.
Right, that makes sense. So to really nail down why the synthetic data works so well, let's look at those ablation studies again. They used GPT-4o as a judge, right, to rate the quality of the generated experiences when parts of DreamGym were removed.
Yeah, that was a neat evaluation. And the results clearly showed the importance of the core components. When they removed the interaction history, the woe history condition, the biggest hit was to causal state consistency. It shows that history is crucial for the model to maintain that temporal coherence, to understand how actions lead to consequences over multiple steps.
Okay, so history ensures consistency over time. What about the reasoning part?
When they removed the explicit chain of thought reasoning, the woe reasoning condition, the main penalties were to informativeness, and there was a big jump in hallucination. So the COTI reasoning is what keeps the generated experiences grounded, factually accurate, and actually useful for learning, rather than just being, plausible sounding nonsense.
Got it. So history for consistency, reasoning for quality, and grounding, it all ties together. Okay, let's try to wrap this up. DreamGym really feels like a significant step forward. It's shifting the paradigm for Agent RL away from struggling with expensive, brittle, real-world interactions.
And towards generating structured, high-quality learning experiences synthetically, driven by reasoning.
And it's not just an engineering trick. They provide that theoretical backing too, right, with Theorem 1.
Exactly. They show mathematically that you can guarantee policy improvement in the real world by optimizing the learning-centric properties of the synthetic data, things like reward accuracy and state transition consistency, rather than needing perfect pixel-level fidelity. Focus on learnability, not just realism.
Now, one limitation they mention is that this work mostly focused on single environment setups.
That's true, which points towards the really exciting future work. So maybe the final thought to leave people with is this. DreamGym has shown we can successfully synthesize rich, structured learning experiences for complex single domains. So the big question becomes, how quickly can we take this approach and scale it up? Could we build a universal world model based on this reasoning-driven synthesis, one that integrates the dynamics of many different environments?
A unified synthetic experience generator for diverse domains.
Yeah, imagine an agent pre-trained on such a model. It might gain the foundational understanding needed for true zero-shot adaptation to completely new tasks and environments. That feels like the next frontier this work opens up.